Hello, today we're continuing in our series on electromagnetic radiation, looking at the effect of electromagnetic radiation on metals. This is all part of the series on electromagnetic radiation where we're looking at what is light, the Poynting vector, the Fresnel equations, polarization, the effect of electromagnetic waves on metals, and waveguides. When we looked at the Fresnel equations, we were looking at the effect of the electromagnetic radiation on dielectrics or insulators. Now we're going to be looking at the effect on metals. And the key point about metals is that the electric field inside a metal is zero. There can be no electric field inside a metal. Even if you produce an electric field by having, say, a very large capacitor, one in charge plus, one in charge minus, such that there would normally be an electric field between the two. If you put a metal in that space, within that metal there will be no E field. That is to say that the potential difference at that end will be exactly the same as the potential difference, or if you like voltage, whatever you want to call it, at that end. There is no electric field within the metal. Why? Because within the metal, unlike a dielectric, there are loads and loads of free electrons. You need to see my video on atomic physics to understand why, but there are lots of free electrons. That's how currents flow through wires. They're metal wires. There are free electrons that can carry the current. So the free electrons inside a metal would always move so as to cancel out any electric field that may apply within the metal. Therefore, there's no electric field inside a metal. There can be a magnetic field inside a metal. The magnetic field does not have to be zero, but if we take Maxwell's third equation, which says that the curl of E is equal to minus dB by dt, this is one of the Maxwell's equations, it's the third of the Maxwell's equations, then you can see that if E is zero, which it is inside a metal, the curl of E will be zero, and therefore there can be no changing magnetic field inside a metal. There can be a magnetic field, but there can't be a changing magnetic field. What then happens when an electric field comes to a metal if it's not allowed to go inside it? The answer is that it falls off extremely quickly, and it falls off within what's called the skin depth, and the skin depth delta is given by the square root of 2 divided by omega, which is the frequency of the radiation. Omega is 2 pi f, times mu 0, which is the permeability of free space, times sigma, which is the conductivity of the material. For radiation of 1000 megahertz, the skin depth would be approximately 2 times 10 to the minus 6 meters. So you can see that the E field will fall off very fast indeed. For light, having a frequency of about 5 times 10 to the 14 hertz, the skin depth is 3 times 10 to the minus 9 meters, which of course is less than 1 wavelength of the visible light. So now I want to consider the situation where an electromagnetic wave, call it a light wave if you like, strikes a metal. Now you'll recall that when we were doing this for dielectrics, we were going from one dielectric to a second, say for example from air to glass. Well, on this occasion we'll consider going from air but now to metal. When we were doing it with dielectrics, we said that there would be a reflected wave and that there would be an angle of incidence and an angle of reflection. And we also said that there would be a transmitted wave or a refracted wave, and that would have an angle of transmission or refraction. Now, there can be no E field inside a metal, and since an electromagnetic wave is made up of oscillating E fields, then there can be no electromagnetic radiation inside a metal. Consequently, nothing can be transmitted. So there cannot be a transmitted part of the electromagnetic field. Whether there's a reflected part or what else happens, we shall have to discover. So let's think about this electromagnetic wave which is travelling in this direction towards the metal. We know that the oscillating E field must oscillate in a plane which is perpendicular to the direction of travel. It's not necessarily just across the paper like that. It can be anywhere in a plane, if I use my hand, in a plane that's perpendicular, or better still if I use a ruler. The ruler is perpendicular, the plane of the ruler is perpendicular to the direction of travel, and the E field can be anywhere in that plane. So let's suppose that the E field is in this direction. In unpolarized radiation, of course, it will be in all directions. But let's suppose it's in this direction. Whatever direction it is, we can always resolve it into two components. And the components I'm going to resolve into are what are called the tangential E field and the normal E field. And I can always do that. And what I mean is, no matter what angle the vector is to the surface of the metal, I can always resolve that into two components. One is normal to the surface of the metal, in other words, perpendicular to it, and one tangential or parallel to the surface of the metal. So it doesn't matter which way this is pointing, the E vector, I can always resolve it into two components, a normal component and a parallel component or tangential component. So that's what I'm doing here. Here is the E vector, and it's resolved into a normal, perpendicular to the surface, tangential, parallel to the surface. And now we're ready, just as we did in the Fresnel equations, we're ready to look at the boundary conditions at the surface of the metal. We've got four Maxwell equations, and here they are. And so we will have four boundary conditions. We'll start with the first of Maxwell's equations, and that says that the integral of E dot dA is equal to the sum of all the charge divided by epsilon naught. This can be rewritten as the integral of E dot dA is equal to 1 over epsilon naught, which is this term here. And instead of sigma q, which is the sum of all the charges, I can actually write that as the integral of rho dV, where rho is the volume charge density in coulombs per meter cubed, multiplied by essentially the volume enclosed. So now we do as we did before, we use a combination of pillboxes and loops. If you don't know what that means, have a look at my Fresnel equations video, and you'll see what I mean. So we take the E vector resolved into two component parts, and we look and see what happens when it reaches the surface. So here's the E vector, here's the normal component, and here's the tangential component. And we're looking to see what happens when that arrives at the surface. Remember that nothing goes into the metal because there's no E field in the metal. And what we do now is we construct our pillbox. And what we're essentially saying is that the E field going out through the area is equal to 1 over epsilon naught times the integral of the enclosed charge times dV. And the trick that you'll remember that we use and that we did before is we call the height of the cylinder or the pillbox dL and the area at the top of the pillbox dA. And then what we're going to do is to shrink this area to an infinitesimally small amount at the surface. So effectively there is no area at the side because that has all been shrunk to almost zero. So what we say is that the normal component, En, will go out through the top. No component of Et, of course, will go out through the top. ET will go out through the sides, but no component of ET will go out through the top, and no component of EN will go out through the sides. And nothing goes out or in through the bottom. That was not the case, of course, when we were talking about dielectrics, but it is for metals because there is no E field inside the metal. This is the metal, and this is air. No E field inside the metal. When we shrink dl to 0, there will be no component of ET going out through the surface of the sides because there won't be any sides to go out through. So the only thing that will happen when the pillbox is reduced to 0 is that this E dot dA term will become the normal term going through the top of the pillbox. So it's En going through dA, and that is going to equal 1 over epsilon naught times the integral of rho dV. But we can substitute for rho dV, that is simply dl times dA, the height of the cylinder times the cross-sectional area. And when dl reduces to 0, that becomes that En dA is equal to 1 over epsilon naught rho s over rho s times dA, where rho s is now the surface charge density, because we're now only talking about the surface because we've reduced the pillbox to such a small size that it's simply almost a two-dimensional object sitting on the surface. So the only charge that is enclosed, if you like, is the charge that is on the surface of the metal, and dA is the cross-sectional area of the pillbox. And that is the first boundary condition. It's not one that we're actually going to use, but we'll derive them all so that you can see them all. Now we'll look at Maxwell's second equation. The integral of B dot dA equals 0. The integral of B dot dA equals 0. We're going to do exactly the same thing. We're going to take, if there is an E vector, there will also be an associated B vector, and that B vector can also be, this is B, the associated magnetic field with the electric field in the electromagnetic radiation. That too can be resolved into a tangential component and a normal component. And then we ask what happens when that field arrives at the surface. So we're going from air into metal. Once again we construct our pillbox. Once again we can say that BT, the B tangential, will go out through the sides, BN, B normal, will go out through the top. This has area dA. When we shrink the sides, when we shrink dl to effectively 0, so the pillbox is simply sitting on the surface, then the only thing that will happen is the Bn term goes through the area at the top. There is no component going out through the sides because the sides have been shrunk to 0, and nothing comes out through the bottom or goes in through the bottom because there are no B fields inside the metal. And so now we've got, using this formula here, that Bn times dA, which is the only thing now that matters, is equal to 0. And that's the second boundary condition. And the obvious consequential of that, of course, is that if that's the case, then Bn must equal 0, because dA certainly doesn't, and the product does equal 0. Now let's look at Maxwell's third equation. The integral of E dot dl is minus d phi b by dt. That is, the integral of E dot dl is equal to minus d phi b, that's the magnetic flux, divided by dt. Once again we take our E vector, which we resolve into its component parts, En and Et. This is the E vector, and we ask what happens when it gets to the surface of the metal. We're going from air to metal again. This time we're going to do the loop because we need to do a walk. It's the product of the electric field times distance. So we now construct a loop. It's a rectangular loop, and we're going to walk round it this way. And we're looking at the E dot dl term. where you've got a dot product, there will be no effect if something is perpendicular to the distance. So when we walk up this section here, from here to here, the only term that will matter is the En term, because that's the one that's travelling in that direction. The Et term is perpendicular, so there'll be no effect of Et, but there will be an En effect. But that En effect will be exactly cancelled by the path down here. So that cancels out. There is no E field in the metal, so consequently there will be no effect for any part of this journey. So the only part of the journey that has any impact is the journey that goes across here, and that will only be the Et effect because En is perpendicular. So what you will get is that Et times the distance L, which is the distance from here to here, is equal to minus d phi b by dt. But now you know the trick, it's the one we did in the Fresnel equations. We simply shrink this distance to 0 such that the loop is infinitesimally thin at the surface. And when this distance shrinks to 0, the flux that passes through the area, which is what this is, reduces to 0 because there's no area for it to go through. So this becomes 0 when this distance becomes 0. And consequently you've got that Et times L is 0. Well, L isn't 0, so consequently Et must equal 0. And that's the third boundary condition. Which leaves us with Maxwell's fourth equation. The integral of B dot dl is mu 0 I plus mu 0 epsilon 0 d phi E by dt. That is, the integral of B dot dl is equal to mu 0 I plus mu 0 epsilon 0 d phi E, that's the electric flux, dt. So now we need our magnetic field component. Here is the B field, here is its components, the B tangential and the B normal. And we're asking what happens when we get to the surface of the metal. There's the air, there's the metal. And once again, it's the dot dl term, so we need to have a loop. We'll need to walk round the loop. Exactly the same arguments apply. This journey exactly cancels out with that journey. There is no B field for any of that journey, so the only thing that matters is this journey, and that's going to be the Bt term because Bn is perpendicular to it. So we're going to have Bt times L, where L is this length here, is equal to mu naught I plus mu naught epsilon naught d phi E by dt, where d phi E by dt is the rate of change of flux through that area, the enclosed area of the loop. Well, you know the trick. The trick is that we now reduce this distance to 0 so that it's a very, very thin loop on the surface. When that reduces to 0, the area reduces to 0, so no flux can go through it. So the whole of this term disappears. That gives you that Bt is equal to mu naught I over L. And I over L is what one might call the surface current density. It's the now just the current density per length, as it were. So you can write that as mu naught Js, where Js is the current density. And that's the fourth boundary condition. So now I want to consider polarized light, polarized in the x direction. I've drawn this diagram many times before. This is the z direction, this is the x direction, this is the y direction, and the E field oscillates up and down in the x direction. The whole thing is travelling at the speed of light in the z direction. Well, we know that's the z direction. Travelling at the speed of light c in the z direction. And there will be, but I won't draw it at this time, an associated in-phase B field, which will be oscillating in the y direction. But let's just think about the E field at the moment. which is an E field oscillating in the x direction. It doesn't matter that it's in the x direction. You will see that unpolarized light will work just the same, but for simplicity, I'm simply looking at polarized light so we don't get confused. What I'm now going to do is to put a sheet of metal perpendicular to the plane of the direction of the wave. So that wave is now hitting that metal perpendicular at that point here. Now, what can we say about the E field? Well, we have a formula for the value of the E field. It equals E0, where E0 is the maximum value of the amplitude, times the sine of kz minus omega t. That's standard form for our wave. And we've got to ask ourselves, what happens to that E field when it hits the metal? Well, firstly, is there an E normal component? That would be a component which oscillates normal to the surface of the metal. Well, clearly not, because the E field is all oscillating in this direction. It is not oscillating at all in this direction. So there is no normal component. What about the tangential component? Well, yes, there's certainly one of those. All these oscillations are tangential to the surface of the metal. The trouble is that we just derived the third boundary condition that says at the surface ET is 0. We just derived that. And what that means is that once that wave gets to the surface of the metal, the E field is completely killed. There wasn't a normal field in the first place, and to the extent that there was a tangential field or parallel to the surface, that is killed by virtue of the third boundary condition. So when you get to the surface of the metal, the E field has gone. The trouble is, there's energy in that wave. It can't just disappear. What happens to it? Well, the parallel that we can draw is a situation where you take a piece of string or rope and you pin it at one end and you say it cannot oscillate at that point. And then you give it a little flick at this end and you generate a wave which moves along the piece of string or the rope until it gets to the fixed point. When it gets to the fixed point, that fixed point cannot oscillate because it's fixed. And so what you find is that this wave comes up to the point and is reflected, but it is reflected upside down. And so the wave travels towards the fixed point, it can't go any further, and it cannot make the fixed point oscillate because it's fixed, so it's simply reflected. And that is exactly what happens with this wave here. The wave comes in, it is killed at the surface, which means you can regard that for all practical purposes as identical to fixing the rope, and then you get a reflected wave. And if this is the formula for the wave which is travelling to the right, then a formula for the wave that is travelling back to the left will be given as E0 times sine kz plus omega t. Right? That is a formula for travelling to the right. This is a formula for travelling to the left. And if you combine the two together, you'll get that the total E field is equal to the wave travelling to the right, which is E0 sine kz minus omega t, plus E0 sine kz plus omega t. And if you look up your identities, you'll find that sine A minus B plus sine A plus B, which is what this effectively amounts to, has an identity that says that ET is equal to twice E0 into sine of kx cosine omega t. A Google search of sine A minus B plus sine A plus B will just give you this as an identity. They are the same thing. And what that is is a standing wave. This part represents the spatial dimension, this part represents the time dimension. We've got a standing wave. What do we mean by that? Well, there's the direction of the wave. Here is the metal, which it hits head on at perpendicular. Here is the wave travelling towards the metal. When it gets to the metal, the E field is killed, but it is reflected. But it is reflected in the opposite direction. And this, of course, is just a standing wave. And it doesn't now travel. The E field will indeed oscillate up and down. So it will go in kind of like this and like this and like this. These will always be out of phase with one another. And there will be points which are called nodes, which will not ever move at all. They will just be fixed. There will be no E field at those nodal points. This is no longer a travelling wave, it is a standing wave. Here is a piece of string, it's actually a piece of elastic, and I hope, illustrate standing waves. I'm simply flicking it, and you can see that the string goes into a standing wave. I'm holding it at both ends, so at neither end can it actually move. The equivalent of the E vector is 0 at each end, but as I flick it, you get this standing wave created. I hope you can see, at least roughly in principle, what I'm talking about. Let's try and understand in simple terms then what's happening. We can only do this in simple terms because you really need quantum mechanics to understand what's happening. Here is my metal, and here is my incoming electric wave, which is the electric part of the electromagnetic wave. When it gets to the surface of the metal, there will be an electron on the surface of the metal. There will of course be an electron over here. There's an electron throughout the metal. This electron knows nothing about this wave because the E field cannot pass through the metal. So this electron is ignorant of the fact that there is an oscillating electric field on the other side. The only electrons that are going to be aware of it are the electrons on the immediate surface of the metal. And when an oscillating E field comes into contact with this surface electron, what is going to happen? What happens when you put an electron in an electric field? It will accelerate, it will have a force applied to it, and it will accelerate in the direction of the E field. So consequently, since this is a changing E field, the electron is simply going to oscillate on the surface of the metal. And that is essentially absorbing the energy of the electromagnetic wave. But what do we know about oscillating electrons or oscillating charges? This is the principle of broadcasting. An oscillating charge generates an electromagnetic wave. And that's the source of the reflected wave. So what is actually happening is an incoming wave is an incoming changing electric field. That changing electric field will cause the surface electrons to oscillate. That will absorb the energy of the incoming wave. Those oscillating electrons then propagate electromagnetic radiation. They can't propagate it that way. Normally, of course, the electromagnetic radiation comes out in all directions, but it can't come out in all directions here because there's no E field allowed in the metal. The only way it can come out is the way it came in. And that is what generates the standing wave. And that is the principle of a mirror. That's exactly what happens. It's amazing. The mirror is made of glass, but behind it is metal. The light comes in from you. The light causes the electrons on the surface of that metal to oscillate, and they generate a reflected wave. And that's the thing you see when you look in your mirror. This also explains how polarizers worked. We talked about those when we did the video on polarization. What a polariser is, basically, is it's strips of metal in what is otherwise a dielectric or insulator, like plastic or something. Now, when a wave comes to a polarizer, and let's take it an unpolarized wave, so it's oscillating in all directions, you can always resolve that unpolarized light into two components, the vertical component and the horizontal component. Now, what happens when the vertical component encounters these vertical metal lines? The answer is it will cause the electrons on the surface of those metal lines to oscillate up and down, and that will generate a reflected wave. So the vertical component is reflected. The horizontal component, however, cannot cause the electrons to oscillate in a horizontal direction because the wires don't go that way. All right, I'll grant you there will be a modest oscillation in the horizontal component because the wires do have a finite thickness, but it's not very much. So it doesn't do very much to kill off the horizontal component. Consequently, the horizontal component goes through, the vertical component doesn't. Consequently, what goes through is horizontally polarized light. And here's an important trick, or here's an important thing where people make mistakes. This is classic kind of wrong thinking. What people think is, here is the polarizer with the wires vertical, and here comes the electric field with its components vertical and horizontal. And what some people mistakenly say is, well, obviously the horizontal component can't go through the bars, but the vertical component can slip through. So the vertical component goes through and the horizontal component gets stuck because it can't go past the bars. That is precisely the wrong interpretation. It is the horizontal component that goes through, not the vertical, because the vertical component can cause the electrons in the vertical wires to oscillate, and that will produce a reflected wave. The horizontal component cannot cause the electrons to oscillate, so the horizontal component goes through. Now, finally, you might ask the question, what about things like gamma rays, which are electromagnetic radiation of very high frequency? They go through lead, and lead is, for all intents and purposes, a metal. How can that be? How can you have a chunk of lead and an incoming gamma ray penetrates that lead, and depending on its energy, several centimetres potentially? The reason for this is something I will come on to in an additional video I will make in this series on absorption of electromagnetic radiation. But in essence, what is happening is that when the incoming gamma ray meets the surface of the metal, the frequency of this gamma ray is extremely high. This is right up at the far end of the electromagnetic spectrum. Very, very high frequency. Here's the electron on the surface, and that electron, if it's going to absorb the energy associated with this incoming gamma radiation, will need to oscillate at the speed of the incoming radiation, and it just can't keep up. It can't do it. And so the wave essentially bypasses the electron because the electron cannot absorb that energy because it cannot oscillate that quickly, and so the wave actually starts to penetrate the lead. It will eventually get absorbed, but by different processes, as I shall describe. There are three main processes. Firstly, to some extent, the photoelectric effect, but more likely Compton scattering and pair production. But that will be described in an additional video that I will make on absorption of electromagnetic radiation.